is Stephen Willson from Iowa State University, who will talk on restrictions on meaningful phylogenetic networks.
This is intended to be a somewhat provocative talk with a word like meaningful, which is so loaded. I'm going to be talking about phylogenetic networks. This was an example of such a network. I want to focus attention on the set I'll call X, the base set. It includes all the leaves, 2 through 8, and the root. The root is 1. The intention is that this base set X contains all the taxa on which we can make direct measurements, and all the other vertices are inferred in some way. We want to learn about the graph from this information on just an X. Now let's look at some of the things which make a phylogenetic tree meaningful. There's a real simple phylogenetic tree. One of the things we can do is look for a most recent common ancestor. So given 2 and 6, we can infer the most recent common ancestor was 8. Or we can try to predict where some character evolved. So if a character is observed at 2, 3, 4, and 5, and nowhere else, then we can make a prediction such as that the character originated at taxon 9. I'm going to write v less than or equal to w if there's a directed path from v to w. So for example, 11 is less than or equal to 4 in this talk because you can get from 11 to 4 by a directed path. But it's false that 11 is less than or equal to 6 because there's no directed path from 11 to 6. What this means is that v is less than or equal to w and can be interpreted as saying that v has the possibility of directly influencing the genome of w. And we're also going to assume that there are no redundant arcs. So for example, we wouldn't have an arc from 11 to 15 because there's already a description in the network which shows the genomic influence of 11 on 15. What we can learn depends upon the model of evolution. I'm going to be talking about 2 very simple models in this talk. C will be the set of characters, and every character in this talk will be binary. So an allele either agrees with the allele at the root or disagrees with the allele at the root. If the set of characters is C, I'll use G to represent the genome. G of 3 equals D8 means that on characters D, E, and 8, the genome of 3 disagrees with the genome at the root, and all the other characters it agrees with the genome at the root. The first model is called monotonic or gene aggregation. In this model, every informative character mutates exactly once. The place where character I mutates exactly once will be written as U superscript I. If U superscript I is 10, then that means that at 10, the character first changed from the character at the root. And the assumption is that all descendants then have that modified character. So that modified character appears at 9, 7, 8, 14, 6, 15, 4, and 5. Nowhere else. Following Baroni, Semple, and Steele 2004, we formed a cluster map, C. What this tells you is all the descendants which are in X, the places where you can make measurements. So C of 11 is 2, 3, 4, 5. Because if the character originated at 11, it would be observed in 2, 3, 4, and 5 under this model, but nowhere else. Those are the places where it can be observed, which are the descendants. C of 6 would just be 6 alone. Let's look at this first example. Here's a network. X is 1, 2, 3, 4, 5. Notice that C of 6 is 2, 3, 4, and 5. Here's easy to get 3 to 4. Here's easy to get to 2. Here's easy to get to 5. But C of 7 is also 2, 3, 4, and 5. So thinking back to what was meaningful for phylogenetic trees, we couldn't tell whether a character which is in 2, 3, 4, and 5, and nowhere else, originated at 6 or at 7 just by looking at genomes of members of X. It's a matter which is hidden inside all the extra vertices about which we have no direct information. Otherwise stated, if you took this network and you combined 6 and 7 into one particular vertex, you couldn't distinguish on the basis of information on X, using this model, between those 2 networks. So I would claim that the more complicated suggestion that you have isn't supported. In other words, to determine whether a character I originated under this simple model at a particular place, you must have that C is 1 to 1. Here's another example, which is a little bit more complicated. Here's a network. You note that C is 1 to 1. Each of these patterns occurs exactly in one place. We want to focus on 2 of them, C of 8 and C of 10. From 8, you can get to 3 and 4, but from 10, you can get to 2, 3, 4, and 5. So 3 and 4 is contained in the set 2, 3, and 4, 5. But notice it's false that you can get from 10 to 8 by a path. You can't get directly there. It's false that 10 is less than or equal to 8. So what could you do? You could insert an extra arc, the red arc, from 10 to 8. And in this case, none of the values of the cluster map change in this new graph. C of 10 is 2, 3, 4, and 5 exactly as before. All the genomes are the same. I claim, using this model 1, we couldn't distinguish between the two graphs, this one and the previous graph, on the basis of information on X. And in fact, this might be a little bit better because it indicates a possibility which exists of the genome of 10 influencing the genome of 8. So the moral is, if G is to exhibit all the genetic influences that could determine the genomes at members of X, then we have this condition that U is less than or equal to V if and only if C of V is contained in C of U. The idea is that the first correction is trivial. If you had C of V contained in C of U and it's false that U is less than or equal to V, you could add another arc, which gives another genetic possible influence. And so your graph was incomplete in that it didn't give all the possibilities. Well, what I've done is motivate a definition from Baroni, Semple, and Steele 2004. The network G is called regular if the two conditions we've talked about both occur. C is 1 to 1, and U is less than or equal to V if and only if C of V is contained in C of U. And what I've observed, perhaps it's not really a theorem, is that if we're going to have the genomes at all vertices determined by genomes at members of X, under the simple model, and is to exhibit all the genetic influences, then G must be regular. I want to push this a little bit further, because I think that that every meaningful graph should be regular. But I think that the model 1 is much too simple. Let's look at a slightly less simple model. I'm going to call a vertex hybrid if it has at least 2 parents. So for example, 15 is hybrid. It has parents 13 and 14. A vertex is normal if it has at most 1 parent. In this particular network, all the other vertices are normal. So what's a first objection to model 1? Well, here, suppose Y has 2 parents, P and Q. Model 1 assumed that it inherited all the modified alleles from P and from Q. But of course, in this situation, we'd expect Y to inherit some genome from P and some genome from Q. In general, you wouldn't get the union unless you had something like polyploidy. So I think that we must allow homoplasies at hybrid vertices. Some of the genome comes from each parent. Another difficulty which I ran into, suppose we had a character which is observed in X but not in Y. Here, X is a normal child of P. Well, we have 2 possibilities. Maybe it originated at X, or maybe it originated at P, but we just said there was a possibility of a homoplasy, so its genome, that particular part of the genome at P was not taken into Y. So this always exists. This is always an ambiguity, and I call that an immediate homoplasy, the second condition, if it appeared at P but immediately disappeared in a hybrid child. So in this particular case, we'd be assuming that in this situation that it originated at X. I'm going to assume there are no such immediate homoplasies. So model 2 has these assumptions. Normal vertices inherit all the modified characters in the parent exactly as in model 1. But at hybrid vertices, it may or may not inherit a character from a parent. And I'm going to assume that there are no immediate homoplasies. So let's look at this particular example. Here's a network. If something originated at 10, well, what are the patterns? Well, every descendant could have that character, and that would give you 4, 5, 6, 7, and 8. On the other hand, there's another possibility. If it originated at 10, it would have to show up in 9, and then 7 and 8 because those are normal. It would have to show up in 14, and then 6 because it's normal, and maybe it didn't get inherited at 15. So you'd have a second possible pattern of where the character could show up. So there's a list of the patterns that might arise. Here's a list of patterns that arise starting from the other vertices. What we can notice is that each of those indicated patterns occurs exactly once in the example. So I'm going to talk about a generalization of the cluster map. The generalized cluster map given any vertex, it lists all the patterns that might arise when something is inherited, possibly at any hybrid vertex. So G of 10 is the collection both 4, 5, 6, 7, 8, and 6, 7, 8. I'm going to call the generalized cluster map generalized injective if no set appears in two different places. And then you might check you don't want the empty set to appear anywhere. And so I would argue that if the genomes of the vertices are to be uniquely determined by information on X under this more general model too, then GC should be generalized injective. And the idea is that if it weren't, you couldn't tell where something originated. So I'm going to argue that a meaningful network, its generalized cluster map should be generalized injective. So how do we recognize such networks? A normal path, what I'm going to call from U to V, is a directed path such that each vertex after the first is normal. So 12, 11, 2 is normal. Because 11 is normal, 2 is normal. 14 to 15 to 5 is not normal. Start 14, but we went through 15, which was hybrid, not normal. So that eliminates that possibility. There's a normal path from U to X if there's a normal path from U to some member of capital X. So there's a normal path from 10 to X given by 10, 9, 7. There's a normal path from 15 to X given by 15, 5. Remember, where you started doesn't have to be normal. Finally, I'm going to call a network normal if from every vertex there's a normal path to X. And the main theorem, perhaps, is suppose G is a normal network, then we get the conditions which I've said were very nice. G is going to be regular in the sense of Baroni sample and Steele, and also GC will be generalized injective. As a mathematician, I like this condition. You look at this network, it's immediate to tell that it is in fact normal. You can just check that there are these normal paths. Therefore, it's regular, which is a really pretty complicated thing to check and extensive, and it's generalized injective, which would otherwise involve computing all those things. So it's a convenient theorem. Let's look at an example where it's not normal. This has one failure of normality. From 7, there is no normal path from 7 to X. But you can check that it's not generalized injective, because from 9, you could get to 2 and 3 as a pattern, but also from 6, you can get to 2 and 3 as a pattern. So it didn't fail. This one isn't good. If you saw a character exactly at 2 and 3, you couldn't tell where it originated. And in fact, there's a partial converse to the other theorem. Suppose X consists only of the leaves and the root. Suppose every vertex other than the root has out degree 0 and 2. So we're just talking about the simple cases, sort of like binary networks. And suppose the generalized cluster map GC is generalized injective, then the network is normal. So you have to have all these normal paths under this very simple condition. So I propose that, in fact, meaningful networks are normal. How complicated are normal networks? Which is an important issue. Suppose that we have a cyclic rooted network, and X, the base set, has n members, including the root. Well, let's look at how many vertices might be in the network. If G is not regular, then that's unbounded. You could have an arbitrary number. You just keep putting in edges as you wish. If G is regular, you can see that it's bounded. It has an exponential bound, 2 to the n minus 1, which is a huge improvement in that there are far fewer vertices. What we're used to is, of course, trees in which V is less than or equal to 2n minus 2. But if it's normal, what happens is that we have a quadratic upper bound, n squared minus n plus 2 over 2. So this is a large simplification. This assumption reduces the number, dramatically, the number of networks that you need to take into account if you're going to be able to interpret them on the simple cases. Moreover, we can talk about most recent common ancestors. As before, I use a strong definition of most recent common ancestor. Most recent common ancestor is something which is a common ancestor, such that any other common ancestor has this as a descendant. So 2, 4 does not have a most recent common ancestor because there are 2 candidates, 10 or 9. You don't have a unique most recent common one. So one property of normal networks is that you get lots of things having most recent common ancestors. If C is the cluster map we defined, C of V has the most recent common ancestor. And there are a bunch of others. If for any vertex that's not in X, you can write it as the most recent common ancestor of 2 members of X. But there are certainly may exist possibilities where the most recent common ancestor does not exist. So you get lots of most recent common ancestors, which were very useful and meaningful in trees, but not all of them. So what might be some future work? We might look at some other properties of normal networks besides the ones I just listed. There are a bunch of others. We might look at other more complicated models. I'll agree that model 2 is perhaps even simplistic, but it's useful. I'm very interested in whether the upper bound I gave is sharp. I suspect not, but I don't know what the true estimate is, the maximum number of vertices in a normal network. And I'm interested in the process of taking a network and turning it into a regular one or into a normal one, seeing what happens. So the summary is that I think that we should be looking for normal networks if they're to be meaningful to biologists. I think if you know what you're looking for, it's easier to find. I've written software which I would not want to show to anyone. They produce lots and lots of networks, and they're garbage. And putting on the constraint that I want a normal network really helps. Thank you for your attention.
Is the ancestral recombination graph a normal network?
Which graph?
Yeah, the ancestral recombination graph. So that is to say, the graphs that represent, recombination history.
It depends. I don't think everyone is normal. I think there's several.
I was thinking that the generalized, what was it? The condition that you can find the birthplace of a character.
Yes.
What was that called? Generalized.
Well, whether the generalized cluster map was generalized injective.
Injective, exactly. Now that condition, it seems to me, was more about calculational convenience than about being meaningful. I mean, in the terms that you discussed earlier.
Well, and under model 2, it's the set of, if you had characters, if you were looking at the characters, and you only had model 2 with no deviations, then you look among the various taxa that you can observe, and every pattern you see, maybe if you had, say, just A's and G's, you look at the places where there are A's, that would be, the taxa in which there are A's, that would have to be one of those cluster sets.
Right. But I mean,
so every one that you observe would have to be one of those. So
sorry. Could you please remind me, this is such a simple question, but what's the time complexity for deciding the network is normal or not normal?
Deciding whether it's normal, not normal. I think it's going to. I think it's going to be linear in n, the number of vertices. It's very fast.
Okay. Thank you.
Yes.
Okay, let's see.
Do you think we should be seeking networks that will work for every single kind of biological process, like recombination, hybridization, polyploidization, or do you think, in other words, you're sort of proposing a class for, seems to me, everything, but maybe depending on the actual thing that we're modeling, we might need different kinds of.
I can well imagine you might have other things. This said that under the simple models, I'd expect these kinds of graphs. And I would probably go a little bit further and say that if you can't deal with the simple models, then it's not going to be very useful. But certainly there are more complicated models in which something else would happen, and I would think that you might get entirely different classes.
You said very early on that you introduced the idea that there might be a path from one of the internal nodes to another, and then you dismissed it, saying if there was another way via other things, you wouldn't have the direct route.
Yes.
You clear with where I am? Okay. I wondered, that one that you said we couldn't have, could in a sense be there if there was some of your information missing. Like I'm imagining we've got species here, and if you hadn't observed certain species, so you'd lost a part of what would normally be a tree or a network, then there would have been an extra path that would include going across the nodes where you said we won't have this one, because you failed to observe other descendants of it.
I'm 100% sure that that could happen. Just as I'm 100% sure if you see a whole human history, there's so much inbreeding that there are things that are happening that you couldn't observe just from the current data, but that actually were there. So I would expect that as you add more data and more information and possibly new nodes adding to X, then those things might appear. So I'm not saying that this is the final version. I'm saying that this is saying as much information as we can currently substantiate.
Okay, thanks, Steve. Let's thank Steve again.